Hello, this is Aykut Attar from Hacettepe University, and today's lecture is on the computation of growth models. So, for this reason, we want to understand um, how the computational experiment is done, how it is designed. For this, we are going to use a classic paper by Kidlund and Prescott, and then we will have a very simple growth model, and we are going to calibrate that model and run some experiments. Okay, so let's start. Um, so there are 5 steps in general um, in computational experiment. First, we want to pose a research question. So this is the question of interest that we are researching about. And then we are going to choose a theory that suits for the purpose, that is suitable for the purpose. Then we construct a model economy using that theoretical background. After that, we are going to calibrate the model economy. For a long time as a student, as an advanced undergraduate and a master's student, I really wanted to know what is calibration. But then I just really learned it during the PhD. So today that will be a very simple introduction to what calibration is. And of course, it will be particularly related to the growth models. And then the last stage, of course, is to use the calibrated version of the model economy to run the experiments, and those experiments, of course, are going to be designed related with the research question or questions. Okay, so in this lecture, I'm going to build again heavily on Kidlund and Prescott's paper. Um, so there are different types of research questions that you can ask using the computational experiment. One type of questions are concerned with the policy evaluation purposes. So imagine that there is a policy, a tax policy, some other type of policy subsidies, or some other stuff. So usually we imagine that they create growth and welfare effects. Okay, and those welfare effects will also be observed along with the distributional results as well. So those type of questions are pretty common in the literature, especially in the macro literature. Then there are questions that we may use to test or to provide some messages about the validness of the theories, so about the validity of the theories. And then we sometimes want to add some um, feature of the reality to a simpler model, and we want to see the effects of such additions. All right. So in general, we can imagine those types of questions, and that is actually about the macro literature in general. All right, and growth models are of course macro models as well, and most of the time we're interested in growth models with microeconomic foundations. So all of these three classes of questions would be relevant for growth economics. Here are some examples from the paper. These are actually real questions, real research questions that are asked and answered in published papers in the literature. So you should just check the paper for the citations of these. What are these papers are? So here are they. What are the effects of current U.S. social security system on capital formation, international equity? Right. So that's one example. And then you see some terms of trade effects and wage rate effects of NAFTA on Canada, Mexico, and United States. And then U.S. tax reform of 1986. And then there's some other type of, for instance, look at question 5. It's about the um, contribution of public finance shocks to aggregate fluctuations, right? So we observe some fluctuations in GDP and inflation and other stuff, and then we want to understand what fraction of this instability or fluctuation is due to actually public finance shocks or oil shocks, as you see in the sixth question. So these are some examples, again, from the paper. In the second step, as I said before in the introduction, we're gonna use a well-tested theory. So we want to choose the correct theory that is suitable for our research question. Now, what are the fundamentals here? So we believe that no model is good enough, of course, to represent all the or many features of the reality, right? So it is different than the real world. But here we follow, and of course, Kittel and Prescott also follows an idea of Lucas. So in his terms, economic theory is defined to be an explicit set of instructions for building a mechanical limitation system to answer a question. So that's a key idea. So we want to create, so we want to use a theory so that a computer can understand that. All right. So each and every step would be entirely transparent to a machine, and eventually, when it runs, it will imitate the real economy. Of course, not all dimensions, but some dimensions that we are interested in. Okay, so that's it. Here, Kittel and Prescott use the example of neoclassical growth theory. So a stochastic version of it, or different stochastic versions of it, are of course good examples, good tools to understand business cycle fluctuations. All right. There's this large literature in macro, starting, to some people's, according to some people, it starts with Kittel and Prescott themselves. But we also know that theory, neoclassical growth theory with exogenous technological progress, is not suitable for development questions. And we also know that from Lucas and Romer and all the early growth papers. So the message here is that we have to choose our theory wisely, all right? So that's an important thing. So we want to sit down after asking the question, after posing the question, we want to sit down and look at the most suitable alternative theoretical framework that best serves our purposes. Okay. So then the construction. So here the big constraint is that, so there's this trade-off between detail versus feasibility, right? So we want our models to be detailed enough so that they truly imitate an actual economy, but also we want to be able to solve these models, and we want to be able to compute these models. So there's a trade-off between detail and feasibility, right? And then, once again, the model must depend on the question asked. Okay? All models are abstractions, but since we are designing our model economy for a particular question, for that question, the model is to be working well. All right, so that's an important dimension. And most of the time, we first use a toy version, a very simple version of a model, to just understand the main dynamic, and then we want to complicate this model step by step to ask and answer more interesting questions. All right. So that's another principle of constructing a model economy in computational experiments. And here is the fourth step, calibration. So calibration in physical sciences. So this is the example again given by Kittel and Prescott. So it means in physical science, it means that it's adjusting the measurement instruments. All right, and here the famous example is the Celsius thermometer here. All right, so as we know, it uses the element mercury, and mercury has the specific features because it's if we put it in ice, it records 0 degrees, and if you put it in boiling water, it records 100 degrees. So it is like so we actually calibrate by using the theory of chemistry and some properties of these elements. Here it's mercury, and so we calibrate this thermometer in that particular way. Okay, and the idea is that, of course, between 0 Celsius degrees and 100 Celsius degrees, it is linear, so mercury expands linearly. All right, so now how can we do in economics? So in economics, our models have parameters, right? So here in the first equation, you see this is actually a vector equation. So you see an equation that tells you that in a model, endogenous variables y and exogenous variables x and structural parameters that are usually fixed, alphas. So here you have y, these are your endogenous variables, x's, these are your exogenous variables, and alphas are structural parameters. So all of these three are vector, and f is also a vector valued function. And model, in very abstract terms, any kind of model could be represented in this way, right? And by solution, we mean writing our endogenous variables in terms of exogenous variables and structure parameters. So calibration in this very abstract framework basically means that we are going to use some values of endogenous variables that are observed, and then some values of exogenous variables that are observed, and then we're going to use the solution of the model. So it's basically the equilibrium relationships, and then we end up with some values of alphas. Not all of them in most of the examples in practice, but some of them will be obtained by using this. So of course, what I am hearing, what I am doing here is that I'm describing what calibration is in very abstract and very simple terms. All right. At the end of the lecture, I will be talking about some other algorithms that are, of course, more complicated than this one. But this is the basic idea. So again, we are going to use the solution of the model and some values of endogenous variables and exogenous variables from the data, and then we end up with some values, some representative or baseline values of parameters. Let me also tell you that calibration is entirely different than estimation. All right, so in estimation, what we are dealing with is actually a stochastic model, and we have the complete set of data, and we have some structural equation or some reduced form equation. So we basically estimate these parameter values from the data using the model or using some reduced form equations. Calibration is a bit different. So in calibration, our purpose is not to find the goodness of it or other stuff. So of course, we want the calibrated model to be successful enough to represent the actual economy, but only in the dimensions that we are actually interested in. Okay. In certain regards, especially in terms of identification, there are more commonalities between estimation and calibration, and I will talk about them also in later slides. Okay, finally, once we ask the question and once we choose the theory, and after constructing the model economy and calibrating its parameters, we actually run the experiment. Okay. So here there is one thing that is important. There are two types of statistics that we can use. One type of statistics will be targeted statistics, targeted moments. So we are going to use those moments to find the calibration. So it's basically, so these are targeted statistics, okay? Because we want to be using them to calibrate alphas, right? And then we must reserve some of the non-targeted statistics to understand whether the model is truly representing reality. Okay. So equilibrium realizations then can be compared with the behavior of the actual economy in some period as well. Okay. And most of the time, of course, these computations are important because we are understanding not just the qualitative answer, but also the quantitative aspects of the answers that we are arriving. All right. So that's usually size matters here, right? So how big is the effect? So it's not just that there's an effect there. So the question is not just whether there is an effect, but how big or small it is. Okay. There's one last thing about experiments, and that's also important in research. So we must use some benchmarks if we are running a couple of different counterfactual experiments. Okay, so I can actually take one example from a paper of mine. In a paper I just written, published in 2019. So I have a model, a growth model that I calibrate for Turkish economy, and then I design some experiments to understand what are the different model inputs that would create some growth and welfare effects. And in one experiment, I choose different parameters of the model separately, of course, in a mutually exclusive way. But in all of these experiments, I choose the experimented value compared to the baseline value by making that the total spending on education expenditures as a share of GDP is just equal to 3%. Okay, so usually, or maybe it was R&D expenditure, I don't remember right now, but so usually if you are using different experiments to answer a question, then you should use a benchmark. So in my case, I would have, let's say, 3 different parameters, each changing the growth rate of the economy to a particular level. So it is important to understand what are the effects of these parameters on the long run growth rate. But when I design these experiments, I have to choose an experimented value instead of the benchmark or baseline value. So how to choose that experimented value? Well, in all of these 3 experiments, I choose the same benchmark. Let's say all these different parameters have experimented values, and all of these experimented values will imply a GDP share or R&D expenditure R&D expenditures of, say, like 3% of GDP. All right, so that type of benchmark will be important. Otherwise, you will be comparing apples and oranges, right? So that's it. That's the very fast course on computational experiment. Uh, of course, you should read the paper to get the main ideas. And there are, of course, other papers, and some papers are pretty explicit about the algorithms that they use in calibration. Sometimes, though, part of the experience goes under the type of tacit knowledge. So everybody knows why they are using it, and the referees know that, readers know that. But sometimes some key parts of the information or knowledge is not shared. So it is important for you to read as many as good papers as you can, and then in time you will learn how to compute growth models and how to calibrate them. So that was the first part of this lecture. Now in the second part, we are going to use a very simple model, a very simple growth model, where growth is based on human capital accumulation, just to exemplify the computational experiment. All right. So the question we are interested in, so maybe I can spend some time on that. So here I'm interested in, and of course this is just a toy economy, but I'm just interested in the growth effects of education subsidies. All right. So in this model, there is this human capital accumulation. Human capital accumulation will be the source of economic growth in the long run, but human capital accumulation requires education expenditures. Okay. So people must be choosing some optimal level of educational expenditure. Then that education expenditure and the adult agents' existing set of skills will create a new set of skills for the next generation. All right. So through that, economy will grow in the long run as a result of human capital accumulation. And here in this model, we're going to introduce government. So government is going to collect taxes in a lump sum way, and then use this tax revenue for education subsidies. Okay, so then the subsidy rate, of course, will be an essential driver of the long run growth rate of the economy, as you would expect. And then we're going to ask what changes in that subsidy rate would create growth effects, all right? Whether there is a large growth effect or small growth effect. So that would be the research question. Okay. And to answer this question, of course, since the question is about education subsidy, we are choosing a theory that builds on this uh, framework of human capital accumulation. All right, so we must be choosing the theory wisely here. So if people is going to respond, if people will be incentivized through these education subsidies, then there must be an endogenous growth mechanism here, and that endogenous growth mechanism must be tied to education. All right, so we are choosing that wisely. And here is the model construction. So time will be discrete, denoted by T here. And the demographic structure will be like 2 generations, but there will be no population growth because every adult has a single child and every child has a single parent. Okay, so once the adulthood ends, then people die and leave the stage, and then their kids will take the stage as adults. Okay. Um, Here's one other simplifying assumption. This is without loss of generality, so we are assuming that population is just 1 or just 1 million or 1 billion. It doesn't really matter because this model has no scale effects. Okay, in terms of endowments, we assume that first of all, every adult has raw labor. Okay, so this is basically time endowment, so they supply this labor inelastically, but they also have skills, all right, human capital. So we denote the average set of skills. Well, this is basically a representative agent model. So the skill of any agent is going to be denoted by HT when that agent, that individual, is an adult at period T. Okay, and of course they're gonna build this human capital when they're in school. Okay, when they're children. In this model, children do not have any endowments, and they don't take actually any economic decision. Okay. So let me continue with the description of the model environment. There will be adult preferences in this model, and those preferences will be represented by this utility function you see here. All right, so here you see the utility function. Now this is a very simple logarithmic utility function, or log linear in some terminology. So CT will be the consumption of the final good. So in this economy, there will be this final good that is going to be produced by a competitive sector, and the adult's consumption or the household consumption in general, so it doesn't really matter, will give utility to the household head. Okay. Also, there is this term. Now, imagine that this is the utility that an adult of generation T obtains, right? And that depends on consumption at that generation, and also the human capital of the next generation. So here we are assuming that people obtain utility from the skill set or the human capital of their children. All right. Why do we assume that? Well, in more general models, we assume that people are altruistic towards their kids, right? And UT plus 1 appear here in this forward-looking term. Okay. Here we simplify such dynamics by assuming that directly adults obtain utility from their kids' human capital. And this is an economic motive actually, because if human capital is large for an agent or for a generation, then income is going to be larger, and then that's good for the kid. And since parents are altruistic towards their kids, that's good for the parent. Okay, so alpha then represents the altruism parameter. Okay, so that's the preference, and preferences are again common. So this is a representative agent model. And now we have two types of technologies. One technology is the production of the final good. The other technology is the production of human capital. All right. And as you see, we are taking the simplest possible technology here. So output of the final good is given in this linear production function of labor. So LT is the raw labor employed, but each worker comes with the skill set HT at generation T, and then there is also this fixed productivity term theta. Okay, that's the production of the final good. So there is no physical capital in this model, but that's fine because we know that since solo capital accumulation itself within a decreasing returns scale framework will not be the source of long run growth, right? Then the production of human capital, we have this production technology for that. So gamma here is some, again, fixed productivity term, but here it represents the productivity of the education technology, right? And ET is the education expenditure. So here we are assuming that this expenditure is made in terms of the final good, all right? And eta is a parameter here. It is a fixed elasticity term. And then we also have HT in the production function of HT plus 1. So what current generation knows, what their skills are, is important for the next generation because they're going to be learning from the teachers in the school or parents in the home, etc. All right? And then we have this constant terms to scale production technology for the human capital. Okay, now up to this moment, I was just describing the model environment, all right? I haven't talked about the ownership structures, I haven't talked about the market structures or the decision problems or the government. Now, we can actually populate this model with aliens, all right? Or we can actually populate this model environment with a socialist government. So we can understand what happens there if we populate this economy with aliens or a centrally planned economy. All right. But what we are going to do instead, we're going to look at a competitive economy where there is a government and government is going to collect taxes and give some education subsidies, and there will be market exchange. All right. So that's the model environment, and after that, of course, we can discuss the budget constraints. So there will be two markets in this economy. One is the market for the final good, obviously, right? So we assume that market is perfectly competitive, and we're going to normalize its price to unity, all right? For all periods, so that will be the numeric good, since in the background that will, so that model will work as a general equilibrium model, okay? And of course, that market will be clearing with this condition, right? Oh, sorry, that's a typo here, because education spending must be also there. Sorry, so there is a typo here. Be careful. I must correct that. I was sloppy basically. So there is this education expenditure there. So it must be CT plus ET. Okay. Then there's also labor market, right? Because people supply their raw labor inelastically. In that market, there will be a wage rate. So the price basically is the wage, and it will be denoted by W. And this market will be clearing in this way. LT will be the total demand. Remember the production function. And 1 is just the total supply because everybody has 1 unit of raw labor, and the total population is just equal to 1. Okay, so now let me describe public policy on education. So government will be imposing a lump sum tax, TT, in each period. Again, this is in terms of the final good. And then there is the subsidy rate, sigma. So this is a constant, okay? And so it will be subsidizing education. So the government will be subsidizing education at that subsidy rate. And then we assume that government has a balanced budget, all right? So the total budget will be TT because, again, there is this 1 billion people. So it will be TT billion tax revenue. And that tax revenue will be spent on the education, so the subsidies on the education expenditure of these 1 billion people, all right? So sigma ET will be the total expenditure by the government, and TT will be the total tax revenue, okay? Now, under these assumptions, household has only wage income, right? And that wage income is spent on lump sum tax, education spending. Now, again, a portion sigma of this education spending is financed by the taxes, and then the consumption expenditure. And of course, since price is normalized, we have just CT here. Okay. Now we can talk about decision problems. All right. So that's important in modeling. All right, first we started with the model environment. So we talked about the time, the model time, what the model time is, and we talked about the demographic structure. We talked about endowments, what those people have, and then we talked about preferences. So we gave our agents some purpose in life, and then we're gonna give them the means of arriving these ends. So those are the technologies. So this is the model environment. Those 5 elements is about the model environment. Then we talk particularly about the market structures, ownership structures, policy, and constraints. Okay, now in the third step, we talked about decision problems because now we can do it. Now we can understand this whole thing as a private ownership economy where there's a democratic government, let's say. So they allow the markets to operate so people can freely exchange goods and services. And what do they have, right? Their endowments. And then out of this, we're going to arrive at an equilibrium, right? So we want to construct an equilibrium using those decisions, the solutions to these decision problems as well. So at the end, we're going to arrive at an equilibrium. So then we're going to find the endogenous variables as functions of exogenous variables and parameters. Okay. So the decision problems, there are 2 of them. One is the utility maximization problem, and the other is the profit maximization of the problem of the firms. So let's first look at the profit maximization problem. So since the production function is linear and wage is the only cost, so we have this. Now we assume that perfect competition, price-taking behavior, free entry. So in such a model, a non-trivial equilibrium with L positive will be equating profit to 0, right? So 0 profit condition will be the equilibrium condition. So solution of this problem is just simple. In utility maximization problem, we have 2 constraints. One is the budget constraint and the other is the specification of the human capital production. So once you put CT here as a function of ET from the budget constraint, and then once you replace HT plus 1 again as a function of ET, then you have a problem that is very simple. It's just one variable problem in education expenditure. And then you're going to find optimal education expenditure within such a framework with public policies. Okay? So that solution looks like that. So in a moment, so let's try to understand that solution. So there's this constant here that depends on alpha and eta. Remember, alpha is the altruism parameter, and eta is the elasticity on education expenditure. Okay, so those parameters are important. Then also theta HT. What is theta HT? Theta HT is equal to wage. Okay, since LT is equal to 1, we have this. So this is the total income. All right, and this is the subsidy rate. So 1 minus sigma is actually the price, sort of a price that that is given for the education expenditure. All right, so you may imagine that this is since it looks like a Cobb-Douglas function. So you may imagine that total income, a particular share of total income is spent on education, and if you put 1 minus sigma here, that's total spending on education, right? And also important is that this is less than 1, right? Because alpha and eta are both positive. So this number is less than 1. So a positive fraction, an interior fraction of total income is spent on education. All right? Okay. Now, since this is a growth model, and since we want to understand growth rate in the long run, we must first write GDP per worker. All right? And it's very simply written there. So since, again, production function is linear, wage is equal to the per capita GDP, and it is equal to theta times HT. All right. Now, if you want to write the growth rate in this economy, the growth rate is proportional. So basically, growth rates are the same because YT and HT are proportional. So GDP per worker is proportional to human capital per worker, obviously, because this is a growth model where growth is due to human capital accumulation. So it is by design, and of course under some simplifying assumptions. So in more general models, you will see a wilder function there. But importantly, growth rate, then, if this is true, growth rates are the same, right? So growth rate of GDP per worker will be equal to the growth rate of human capital per worker. And if we put education this is the optimal level of education expenditure. So if we put this back into the human capital production function, we arrive at this one. Okay, so that would be the endogenous growth rate of this economy. Okay, and it depends on gamma, eta. So the gamma and eta are education technology parameters. I might have a typo here. Yeah, I guess no. Okay, no typo. Sorry. So alpha, again, altruism parameter. Eta is the elasticity of human capital in the next period with respect to education expenditure. Theta is some productivity term in the production function. Gamma is some productivity term in the human capital production function. And sigma is the subsidy rate. Okay, so it depends on what? 1, 2, 3, 4, 5 parameters. Okay, so those 5 parameters are actually the parameters to be calibrated. So now we can start talking about the calibration of these parameters because we want to compute the equilibrium path of the economy. And of course, since this is a short lecture, I am basically passing through all the formal definitions of general equilibrium, etc. So you can see those in papers or in textbooks. But now I am taking a very shortcut there. So since this is a very simple model, I actually solve for the growth rate. So if I know the initial values, then I can simulate the entire economy. Okay. So one typical assumption in growth models is that state variables, endogenous state variables, for these variables, the initial values are usually given. So here, that particular key endogenous state variable is human capital per worker, and we assume that H0 is exogenously given. And then here comes the most difficult question. Are all parameters identified? So here, identification is not the same thing in the econometric sense of the term, but similar, right? So the question is that, can I learn the values of these parameters from the data? So in that sense, they are the same thing. So remember the calibration algorithm. So here I basically assume that if I know some values of y, some values of x's, and if I know the solution, then I obtain some of the alphas, all right? So this means that only some of the structural parameters are actually identified through the data and through the model. Okay, some parameters may remain unidentified, and then of course I should then develop other strategies, and there are other strategies that I will explain in a moment. So in that model, in that particular example, not all parameters are identified. So the answer is no for this particular example, but then we will have again some strategies. So in all models that you want to compute in growth economics, you also must be careful with timing, right? So remember that this is a model of overlapping generations, so length of a period is actually long, all right? So usually it is taking like 20 years, 25 years, and here we assume that it will be 25 years because it will be the lifetime of one generation. So the total lifetime will be then 50 years. Now, how do I learn about the subsidy rate? Okay, so that's a key question because I assume that the real economy that I observe, and here I'm focusing on the US economy basically, the real US economy I observe is an economy with education subsidies, right? So benchmark value of education subsidy will not be different, so will be different than zero. Okay, so when I do a quick search, I found some data for the year 2002, and that data suggests that for the higher education, though, it will be 23%, right? That subsidy rate. So this is I think a researcher at MBER. So we have so as you see, the model counterpart for that is total education expenditure, and within total education expenditure, what is the subsidized education expenditure? Okay, so that data basically pins down what sigma is. All right, so that's good for the a toy model that is used for educational purposes. Now, next we are calibrating theta, and we're gonna use the definition of GDP per capita for that. All right. So remember that GDP per capita is an endogenous variable of the model, YT, and it will depend on the endogenous state variable HT through this solution. Okay, so theta then can be obtained under what condition? Under the condition that we observe GDP per capita or GDP per worker, and we observe human capital. Now, observing human capital is a difficult issue in the literature. So there are numerous papers written on that, and some of them are actually written by my advisor Lutz Hendricks. So you may check his papers. But here we are going to use the Penworld tables data. So in the Penworld tables, you have RGDPO. So this is real aggregate GDP. And you have population data. Again, this is for year 2002. And then this is GDP per capita. And then if you divide GDP per capita to human capital using this equation, then you find this number. Okay, and of course, since we are not imposing any constraints on the measurement units, theta is a large number. Okay, it doesn't really put any bearing on the growth rate. Okay, because education expenditure will be normalized accordingly as well. Okay, now here as you see, as I said. So now we also want to understand other parameters, and we want to use any type of relevant knowledge, any type of relevant statistics from the data. And what we found here is that in the year 2000, 5.8% of GDP is spent on educational institutions. So this is the total. Okay. The first one was higher education, but we can assume that that particular rate is actually applied to the entire economy, or we can assume that that particular educational technology in the model is for higher education. So it is, of course, not very straightforward to take a model to the data, but we can do our best. So in this model, one simple strategy is to take the total educational expenditures as a share of GDP, and that particular rate, that particular ratio is 5.8%. So in the model, it is ET divided by theta HT, right? Because theta HT is GDP and ET is the total education expenditure in the economy, right? So that ratio in the model equals to that. All right, so that's coming from, again, the optimal education expenditure. And in the data, it's equal to that. All right, so then if you put the information sigma that you found earlier, okay, here, sigma, this means that you can actually solve this equation, okay? But you can only solve it for alpha times eta, all right? And here is the result. Alpha and eta are not separately identified, okay? So in other words, not all parameters are identified. So if I want to identify alpha and eta separately, and for some purposes in the experiments, I can actually need them. So then I have to put additional information, additional data about the elasticity parameter eta and the altruism parameter alpha. Okay, I'm going to show you just in a moment. But importantly, if 5.8% of entire GDP is spent on education, then alpha times eta for this economy must be equal to 0.0467. Okay, so that's the idea. Now I know, at least I know alpha times eta, what alpha times eta is. Okay, now how to put more information? Well, in general, we have two strategies. Either we're going to look at the literature that offers a value, a calibrated value for one of these parameters. Okay, and this is used very frequently by many researchers, but careful ones and good ones, of course, look at the examples that use the same functions, same production function, same utility functions, etc. All right, because there must be some overlap between the two papers. If you are borrowing some value of a parameter from another paper, you must be careful, all right? So here we can use actually Delacroix and Gosseri's paper because they actually use the same human capital production technology and they calibrate eta for a typical, developed economy as 0.53. Okay, and if we use if we follow strategy one, and if we use that value for eta, then alpha is implied as this. Okay, 0.08. The other strategy is to exploit the feature that eta is a bounded parameter. Okay, alpha is not, because alpha takes values from 0 to positive infinity, but eta takes values between 0 and 1 in this model. Okay, so we can actually use this alpha eta result, and we can use different eta values between 0 and 1, and we can look at the model results for different values of alpha. Okay, so in some models, especially if we cannot find outside information, we can actually exploit such features of the models. Okay, here for the rest, we are assuming that, yes, we are assuming that this is true, because here okay, for the results of this class, for the slides that I will discuss in the rest of the lecture, that actually makes no difference, okay? Because I'm going to only use alpha times eta, and I already got it, right? I already got alpha times eta. So the remaining parameter is gamma, and gamma will be calibrated with a particular target of growth rate, okay? This is again a typical thing in growth economics, growth economics, because usually we have this observed growth rate, right? And in the U.S. economy, that glorious number is around 2%, 2% per year. But remember, T is not a year in this model. T is 25 years. So we must convert that annual target to a generational level, okay? And that's the simple formula that you can use, because if the growth rate is fixed at 2%, and if 25 years pass, then that would be the growth rate from t equals 0 to t equals 25. Okay. Then, of course, I will use the growth formula. This is the formula that I derived here, you see. So this is the growth rate of the economy. So that growth target in generational terms, so this is growth rate of GDP per worker per generation, it's 1.64. This target implies a gamma of nearly 5%. Okay, so now I have all the parameters I need. Why? Because what I ask here is the effect of sigma. Remember, the subsidy rate. Okay, so how does the growth rate change when the subsidy increases by 5 percentage points? Sorry about that. So 5 percentage points. Remember, the baseline value was 0.23, and 5 percentage points increases 0.28, right? So now, since I have all the parameters, and since I have the growth rate formula itself, I can actually calculate an alternative growth rate. So this is the experimented growth rate that depends on all other parameters, alpha, eta, gamma, and theta, but now subsidies change. Subsidy is now larger. Okay, and then I can compare it with the baseline value when we obtain under the subsidy rate of 23%. Okay, we can also check how the GDP share of education increased or decreased, right? So if you go there, what is that? That's here. So HT will be growing faster, right, because of higher subsidies. And then what happens to ET? All right, what happens to ET divided by theta HT? So that will be another interesting moment. And finally, since this is a simple model, and since we can calculate utility, as in here, we can actually look at the welfare effects of subsidy changes. Okay, that's it. So these are some simple experiments that you can run But again, the main research question was what happens to growth rate when we increase the education subsidy. I will also describe another experiment, so that's also relevant. We may actually imagine some education reform. So imagine that instead of increasing subsidy rate to 5%, we use that particular difference to increase gamma. All right. So we would imagine an educational reform technology. So once the government spends that money on infrastructure or technology, then gamma would be larger. Okay. Then we can actually of course, we need some benchmarking here. So you have two different policies that increase the growth rate by the same amount because we're going to choose a gamma increase that matches the growth rate G1. Okay, remember G1 was the growth rate when we have increased the subsidy rate. Okay, now instead of increasing subsidies, we can increase gamma as well to imply the same growth rate. And then we have two experiments. One is on the subsidy increase on education expenditure, and the other is not increasing the subsidy rate, but uses that tax revenue to some educational reform. And that educational reform increases the productivity of the human capital technology. All right? So then we can compare these two policies for some third dimension. Okay? For welfare, for instance. All right? So which policy is better in terms of welfare? So as you see, running experiments and answering some questions would lead to some other research questions that you might be interested in. And those questions, once we have public policy in any growth model, different set of experiments could basically signal you, could basically blink an eye on you, and you can actually develop answers to them. Okay. So I have a few remarks before conclusion. Make sure that this is the simplest, most elementary view of computation in growth economics. All right. Here, both the model is simple and the question is simple. But if you ask more interesting questions, then the model must be more complicated, and then the calibration algorithm, of course, must be more difficult. There are good examples in the literature. At the end of the semester, we're going to cover one of my papers, which endogenizes almost everything for the Turkish economy and try to understand what actually drives Turkish economic growth. One thing is much more important, especially for the 21st century macroeconomics. Right now, heterogeneity is the hot topic, and unless our models could be extended to heterogeneous households or heterogeneous people, then we cannot understand inequality. And inequality is everywhere in the real economy. So the problem is that once we introduce heterogeneity into the models, even if the theoretical part is easy, computation part is entirely a different game. In the next years of your study, you will see, I'm sure, some challenges in that regard as well. But there are some algorithms that work. People are writing codes, computer programs that you can actually use, etc. But that's the most interesting and most difficult part of growth economics itself. Okay, that's all for this lecture, and thanks for watching.